Hello, welcome to this introductory series on reactor physics. My name is Terry Price. I'm studying in the field of reactor physics, and I hope with the series gives me a chance to sort of improve my own understanding of the subject and maybe explore a bit. And there's that, and the other aspect is the quality of reactor physics material I've seen available out on the internet. It doesn't really in terms of videos, a lot of it doesn't quite mesh with me, and I assume if it doesn't mesh with me, it doesn't mesh with some other people. So I hope that someone out there somewhere gets some sort of benefit from this beyond my own understanding. So let's talk about reactor physics. Any sort of discussion of reactor physics inherently is a discussion on neutron behavior. And I assume you've taken some sort of introductory course on, or done some introductory reading on nuclear reactor physics. And you know that neutron is a neutral particle of about 1 AMU mass, and that it can either be conceptualized as a billiard ball type device or entity, or it could be a particle, or there's also the wave representation of the neutron. Both of these representations are important or maybe I should say utilized in the study of reactor physics, but for the purposes of our initial studies, we're going to primarily focus on the point-like behavior of the billiard ball-like behavior of a neutron. So if we imagine the neutron as a billiard ball for our initial purposes at least. So reactor physics can be roughly broken down into two sort of broad categories. We have our statics type category and our kinetics or kinematics, this is sometimes called. And under kinetics, there's also sort of what we call sometimes referred to as the dynamical behavior of the reactor. And the statics, this refers to the steady state behavior of the reactor, whereas kinetics, this is the time-dependent behavior of the reactor. And when we talk about dynamics, we're talking about the kinetic behavior with feedbacks such as temperature or density or something like this, or even thermal expansion. So that's sort of the broad overview of the subject. And what I'd like to talk about today is first like to talk about the state space of a neutron, and then I'll go into a brief discussion about what we mean by the neutron flux and the neutron density. So the state space of the neutron, if we imagine our neutron, what ways in which can the neutron's behavior change? Well, the first thing we can do is we can assign a position vector r to the position of the neutron. We can also have some sort of direction vector omega. This is in three-dimensional space. And we can also talk about its energy. And we can also talk about the behavior of all these variables in terms of time. So we have the state space consisting of the collection of a position vector, the energy, the direction omega, and the time. These are sometimes this time variable is ignored in steady state, so we have what's sometimes referred to as a 7-variable 7-variable state space. So we have our 3 position variables, our energy, our if we're talking about spherical coordinates, our phi and theta, and time. Well, time would be the 8th, but let's assume we're working on steady state. So we have these, and these are packed into our position vector, and we have these guys here. Sorry, just these guys here, and these are packed into our direction vector. This is spherical coordinates. You could also parameterize this in terms of Cartesian coordinates, a Cartesian direction vector. But from what I've seen, it's mostly spherical. I should also mention what reference material I'm using here, just as an aside. I'm using Carl Ott's book, Introduction to Nuclear Reactor Statics. As sort of a guide. I'm going to try and digest this material as much as I can for you guys. But when I initially learned reactor physics after my undergraduate experience with it, it was from John LaMarche's book, Introduction to Nuclear Reactor Physics. So I'd imagine that much of my understanding would be highly tainted, or not tainted, but highly filtered through that understanding. So that being said, so that this is the state space of a neutron within a nuclear reactor. It's 7 or 8 dimensional, or 2 vector variables and 2 scalar, or if it's steady state, just 2 vector and 1 scalar. And how I sort of imagine this is, well, let's actually talk about the neutron density function, and that'll sort of lead into that discussion about where the information comes from. So we have what's called our neutron density function, and just for the sake of clarity or simplification of the discussion, we're going to omit the t here, the time dependence on it, although all these sorts of things could be a time dependent function. So we have n, this is our number density of neutrons, and this is neutrons per centimeter cubed. So if we have a cubic volume measuring 1 centimeter by 1 centimeter by 1 centimeter, what is the how many neutrons are within it? And this is parameterized by our position variable, our position vector, our energy, and our direction vector. And what this gives is the number of neutrons per centimeter cubed. It's a probability density function. So this is the neutron density, and it's a type of probability density function. It's a probability density function of its neutron state space. So how I like to imagine this is that this neutron density function, this is a mapping from this 7D, and when I say 7D, I'm referring to, of course, this being 3 and this being 2, 7D space into sort of a 3-dimensional real space. And what it does is it maps every point in this real space, or it maps every point in this 7-dimensional space to a point in this real space. So it tells you this N is the map. This N tells you where a neutron is in terms of R, its energy, its position, and its optionally its where it is in time. So that's the neutron density function. Sorry, let me just erase the screen here. So let's talk about, so now that we have an understanding of the neutron density function, let's talk about flux. And we write flux in reactor physics with this phi symbol. And if we say phi equals the neutron density, and I'll just leave out the parameters of the neutron density function, and we multiply that by the velocity of the neutron, that particular neutron. You can actually write this out in long form as phi as a function of the state space see now why I didn't write it like that. It takes forever to write. Times the magnitude of the velocity. And the velocity for a neutron is related to the energy via the relationship E, of course, equals 1/2 mv squared, where m here is the mass of the neutron. So that is the definition of the flux. And how this is usually interpreted is if I have interpretation is if I have a volume, a unit volume, let's say. Sorry, and I actually forgot there should be a little vector arrow because velocity is a vector valued function. If I have this three-dimensional volume here, and I were to, and it's going to have some neutrons moving about in it. Now, if I were to set a stopwatch, and this is, of course, unit volume here and unit volume there. If I were to watch this for 1 second, and each of these neutrons, as they travel about this volume, they trace a path in the volume. What the flux gives you is the amount, the length, the total path length of this neutron, the total path length traced out by the neutrons in the volume in 1 second of time. So it's the path length generated per unit time. And that kind of makes sense from our definition here, because if we were to sort of multiply this here by, if we said in V, and of course we can multiply any equation by unity without changing it, and we multiplied this by 1 second, this would give us velocity times a time equals a distance. So that's the path length, the path length generated times the number of neutrons generating that path equals the total path length. Okay, so that's the interpretation of the flux. So we can talk about the, and sometimes this flux, this is referred to as the angular flux. And what we can say is we can sort of collapse this or concatenate this in terms of different variables. So this is the angular flux when it is a function of r, e, omega, and t. And what we could do, for example, is we could integrate the angular flux over the domain of all the directions So we're adding up all the directions, and we're getting the what we call the energy dependent flux. Sorry, I should write that as, or let me actually erase that. Should write that as phi of r. Sorry. Phi of r e and optionally t, which is a better notation for optional parameters. So that we call this the energy dependent flux, in that it's only a position of position, energy, and optionally time. Sometimes you'll call this the energy dependent or the time dependent energy dependent flux, or time and energy dependent flux. And then probably most generally we have just the neutron flux, phi of r. And phi of r is just the integration over all the energies of the energy dependent flux. And this is for your sort of beginner level problems. This is the probably the most common group or common thing you'll use. Now, just a sort of an interpretation of these integrations. Notice that these integrations, these are with respect to state space variables rather than physical or positional variables. And this is something that really kind of messed me up when I first started in this field, was that the integration, the sort of interpretation of these functions is that you have this sort of amorphous 7D space, and we're mapping this to a three-dimensional space. So what we're saying is if we take like a cubic volume in our three-dimensional space, and we fill this up using our phi function here with neutrons, we're filling it up with everything in the omega, so all values of omega. And you can almost think of this as like this having like a Excel table, and the Excel table has entries for R, E, omega, and T, and then a flux for each of those. And what we're doing when we're integrating is we're adding up everything that matches here, here, and here, but the wild card match is sort of on this omega here. Maybe I'll do a video later sort of demonstrating that, but I hope that's clear. So that's the energy dependent flux, and just what's sort of colloquially referred to as just the neutron flux. And this is, of course, the angular flux, phi of R, E, omega, and T. There's a special case. There's a special case in which what we have is what's called an isotropic. Let me write that. An isotropic flux. And in an isotropic flux, what's happening is the angular flux, it's uniformly distributed across all angles. Or that is to say, there's no variance. If we plotted out the neutron population with respect to direction vector, it would remain flat. So there's no variance in the angular distribution of the neutrons. There could be variance in the positional or energy dependent variation of the neutrons, but they're all moving equally. There's an equal probability of finding a neutron at any given direction vector, because remember we're talking about probability density functions here for flux and neutron density. And what we can say here is, in this special case, the angular flux, and I'll omit the time variable here just for simplicity's sake, the angular flux this equals to 1 over 4 pi times the neutron flux, or just the flux. Because recall that there is in a given sphere there are 4 pi steradians, and maybe I'll get into solid angles later. So the probability of finding, so given an infinitesimal area of this sphere, the probability of finding a neutron going in that direction is just 1 divided by 4 pi, or 1 over the total area. So that's the isotropic neutron flux, where we relate in the isotropic case, we relate the angular flux to the neutron flux by the factor of 1 over 4 pi. The final thing I wanted to touch on in this video is the energy groups. Of a flux. So we have we can write phi of r. This is the total neutron flux, and this is equal to the integration from 0 to infinity of the energy dependent flux with respect to energy. Then we have what's called the thermal flux, or phi sub th, and this is equal to, and it's a function of position, and this is equal to the integration from 0 to what's called the thermalization energy, or thermal energy, of phi of r dE. And as a rule of thumb, what they say is the thermal flux is approximately equal to 5 times the Boltzmann constant times your material temperature. And this is from your study of statistical mechanics, where if we have something in thermal equilibrium, it assumes what's called a Maxwellian distribution. And finally, we have the fast flux. And the fast flux is, we denote this with a phi sub f, and is a function of position. And this is equal to the integration starting at the thermal energy to infinity of phi of r e dE. And we can get into neutron temperatures later. I mean, you can break this down into more, but these are sort of the two basic energy groups. There are more energy groups we can talk about. In fact, let's just go ahead and knock that out right quick. In general, there's a convention that if you have the neutron spectrum, here spectrum meaning energy, this can be broken down into groups, finite domains, and we can start at 0, 1, 2, 3, 4, so on and so forth. And we can call it the fastest at 0 convention. I don't know if anyone else names it that, but it's used in Lamarche's book and every other thing I've seen, where the 0th energy group, this is where the fastest neutrons are, and there's slower neutrons as you climb up the number of energy groups. So we have fastest here and slowest here. And in general, you can find out how many neutrons, or what your flux is, in the gth energy group by integrating between, here's your upper bound and here's your lower bound of phi r e dE. We call this is under the study of, or in your indexes, energy groups. And you can have as many energy groups as you want. One popular one is the and there's structures for energy groups. There's the WIMS energy group structure, which you might get to if you study computer codes and reactor physics, and that's 61 energy groups. But for most problems, we're just going to have 2 energy groups, or the so-called 2-group approximation, which we have just fast neutrons and neutrons which are at thermal equilibrium with their surroundings. So, and I'll talk much more about thermal neutrons later on, but that's sort of a basic overview of the neutron state space and the flux.